Um, so there are several things to take note of. We've set up a Slack system. Slack is something that you can use for chatting and asking questions and so on. And we've got a link to that. So the link for all these things you can get by just sending a blank email to this email address up here, and you'll get something like this down here at the bottom of the screen. Okay. Here's Slack. So if you join Slack here, you can talk directly with us and with TAs. Recordings are also available. And again, if you just send a blank email to this email address, you can get a link directly to the recordings here. And we're also putting all materials in Dropbox. And here is the Dropbox link. So go ahead and send it any questions like you did before, if you have any about these items. Okay. Also, make sure that if you have a mic on, that you turn it off while we're lecturing and so on, so you don't get a lot of feedback. Okay, so last time I had been talking about basic elements of writing computer code in Python, so to get you guys started. Maybe before I go on, there was a question about whether the for control structure is limited to this simple way of just iterating through integers. And the answer is no. You can do fancier things. So, for example, if you don't want to just step through integers one by one, then you can do some other things. Well, let's do some examples. So, say that I want to do an iteration that doesn't start at 1. I can start at, say, something like 2. What am I doing wrong here? I didn't run Python. For I in range 2 to 10. Don't forget the colon. Print I. And you start from 2 rather than from 1. Okay, say that you want to go through steps not of just 1, but say you want to jump by steps of 2. Then the last entry in those parentheses tells you how many steps you want to jump. So we can do something like this. I. Now we go 2, 4, 6, 8. Like that, we skipped the 9 because if we went from 8 to 10, we get to 10, and that's outside of the range described by range. Okay. You can actually do even more general things. So let's say that we've got a list. Remember how lists work? Let's make a list of letters. O, M, and G. Okay. That's in the list that I've called lets, O, M, and G. I can actually use for that. For I in, now what I'm going to do is range I'm going to take the range to be the length of this list. So len tells you the length of the list. The length of the list lets is 3. Oh. Now let's print what's inside of that list. Okay. We could also print, say, an exclamation mark. Maybe think for a second what you expect that to do. Hopefully it doesn't give an error because it's always embarrassing. Okay, it prints O exclamation mark, M exclamation mark, and G exclamation. So those are a few more examples of how you can use for. Okay. And just to answer another question last time, there was a question about resources for some of the topics that I discussed, specifically topics involving quantum chromodynamics, nucleon structure, and so on. So I've actually got a list of articles and references and books and so on that I sometimes give to people who are interested in this topic. And I have provided here a link for you. This is on the main page. Let me just point it out to you so you know where it is. Hope I still have it up. Okay, so if you go to the main Python for Physics page and you go down to this question that was asked last time, do you have any references and articles for beginners? Here's a PDF with some things. We've got some simple sort of pop science article level, introductory article level things here that you can go to. Some more advanced things as well. And maybe I'll update some of that as we go along if I can think of anything else to put there. Go ahead and ask questions if you have any about that. Okay, so let's keep going. The one set of slides I didn't get to last time before I quit was slide about functions. Okay, many of your programs will be organized around the concept of functions. So anytime you take something and return something, basically talking about functions. So anytime you want to set up a function, here's the basic nomenclature in Python. So you have definition, say def for definition, you have a function name, then you've got some argument, and then don't forget that when you do a function like this, you need a colon at the end here. So we've got the def, something that says we're going to define a function, we've got the function name, and we've got the arguments of the function. In the body of the function, the way we separate sections of Python code is using indentations. So remember to push tab to indent in. And then you've got a set of instructions. So this function that I'm defining here is a function to convert temperature in Celsius to Fahrenheit. So you're going to give the function a temperature in Celsius. So Ctemp is my identifier for a Celsius temperature, and return a temperature in Fahrenheit. And here is the algebraic conversion relation. And then at the end of the function, well, first of all, I put a circle here. One of the common mistakes is to forget that colon. We've got the operation here. Then you return whatever the value of what you want to return is. So in this case, I calculate the temperature in Fahrenheit, and that's what I want to return. So let's maybe see how that works, go ahead and open up my terminal. And you can try doing this yourself in a terminal, or if you want to get practice with Anaconda and Jupyter, you can do it there. So let's do def cell to var, that's Celsius to Fahrenheit, C temp, colon, and then temperature in var is equal to C temp times 1.8, that star is the multiplication operation, plus 32. And then let's return tvar. Okay. Now let's try putting in some temperature in Fahrenheit. Or in Celsius. So a temperature in Celsius of 60 degrees. Okay, 60 degrees for those of us who work in Fahrenheit sounds like a pretty nice day. But if you convert it to Celsius, it's convert the Celsius to Fahrenheit, that is, it turns out to be something swelteringly hot. Okay? So that's an example of a function. And go ahead and ask questions if you have any. And you'll see that most of our programming will be organized according to functions. You'll want to do that in the project that I give you here in a little bit. Okay. So one of the things that I mentioned was great about Python is the extensive amount of existing software that it has available. So libraries, for example. One of the things you'll notice at the beginning of many Python codes are imports of these various libraries. So the most common ones are, say, NumPy, and you see, let me start slides again. You see lines like this. Import says you import, okay, a library called NumPy, and then we say as np, because when we use libraries like this, so here's what it looks like in the code, okay? We access functions inside the library by using a dot after the name of what we imported. So in this case, I named the imported library np, just to be a shorthand for NumPy, and pi is just the constant that you're familiar with, 3.14159, blah, blah, blah. Okay. So here's a set of operations that I do with pi. And you just do this directly like I've shown it in the Python code. So if I want to have a number pi that I use everywhere, I will go import numpy as np. Okay, so now I've imported numpy as np, and then np.py, that's this number. And then if I want to make the identifier PIE equal to that, then I'll say something like this. And NumPy also includes functions like the sine function, the trigonometric function that many of you are likely familiar with. So we can do something like this. Sine of pi over 2 is, in radians, 1, and that's what that gives. And all of these libraries come with detailed descriptions of what they contain, so I've provided links for you there. Okay. The other tool that I wanted to mention, some of this has already been discussed, but helpful to discuss it again, is Anaconda, which includes all of these utilities here, including Jupyter, which we've discussed already. Okay. It's a graphical user interface that allows users to launch applications and manage Conda packages. Okay, so Conda is a utility that allows you to use many existing packages. So go ahead and do a search for that, and you'll find a description of what Conda is. Conda is an open source package management system and environment management system. Okay. Jupyter is what we've been using a lot. Okay. Jupyter allows you to create and store long Python codes in a notebook form. So this is what a Jupyter notebook kind of looks like. You see the importing of various libraries up here at the top. You see a function being defined. And so unlike in this terminal set of calculation, I lose everything once I close the terminal. Here I store everything. And I can run it very much the same way that I would use some symbolic calculational package like Python. So I like to think of it as mathematical with Python. Okay, so that's really finishing up everything that I wanted to say last time. And now we're going to get into doing some actual projects together. So I'm going to ask everybody watching to start trying to do their own thing, and we'll be here to help out. Okay? So I've got a few suggestions for some warm-up mini projects. Okay? They'll be especially good for those of you who had at least a little bit of physics, and maybe some of this will be familiar to you. So I'm going to suggest several things. So if you're really still struggling with just setting up, Jupyter and figuring out how to use these basic Python commands, we'll set aside a breakout room with somebody to help you there. So we'll have one breakout room to help people who are really just trying to get going. And then we'll have another breakout room with help for a specific project that I'm about to describe. A project involving projectile motion, which is one of the staples of introductory physics classes. Okay, and then eventually we'll get to one that's maybe a slightly more involved after that, one involving elastic scattering of subparticles. Okay. So let me just describe this second project here a second, and then we'll move into breakout rooms. So,
Ted, you have some questions. I don't know if you want to answer some of these now, or you want to maybe answer them later.
Are they really urgent questions?
I don't know if there's. That I think would have been relevant to what you were talking about before, that I think might be an issue that people are struggling with. This is by Amar Abuchukur from Amman, Jordan. And the question is, how can we make the program ask for an input for the function? And so I think this might be,
that might be something good for a breakout room, I would say.
Okay, sounds good. Yeah. Maybe just fleshing out more the definition of functions, inputs, and what are the outputs in one of the breakout rooms, I think would be useful for others.
Yeah, I think so.
That's good.
Yeah, I'm reluctant to go into too many details of Python coding here because then we could just do it forever and not get to a novel project. The best way to learn this stuff is by doing it. But of course, we can answer all those questions. It's probably just better on a case-by-case basis.
Okay, sounds good.
Okay, so let me just give a description of this project that I have in mind. Okay, I hope at least some of you have seen two-dimensional motion with a constant acceleration. Most common example of this is projectile motion. Okay, so here is a set of relevant equations. So if I've got an x position as a function of time, and start with slides again. I've got an x position as a function of time with some initial x position, some y position as a function of time with some initial y position. Then their later positions are given by these equations, where we've got an initial velocity in the x direction, an x component of velocity equal to v0x, and an x acceleration, a subscript x, and similarly, y component of velocity equal to y, or v0y, and a y component of acceleration equal to y, a subscript y. So if the acceleration is 0, then it just becomes position equals initial position plus velocity times time. You've got a quadratic term here if you've got non-zero acceleration. Okay. Velocity, you can also keep track of the velocity of these particles as a function of time. And if you know calculus, don't worry if you don't know calculus, but if you do, it's just obtained by getting the derivatives of these first equations here. Okay. But otherwise, it's just velocity in the x direction is equal to the initial velocity in the x direction plus x acceleration times time, and similarly for the y component. Displacement is the difference between the whatever final position in the x direction or final position in the y direction you're interested in, and the initial x and y directions. So I'm just going to introduce that notation. And then finally, if you know the displacements and if you know the accelerations, there's a quick way to get the x and y components of velocity at any given time. Okay, so the first step is to remember from last time, the first step is to establish what our equations are, what basic physics principles we're interested in. So I make a special slide to do just that. And now we ask, well, if we're talking about projectile motion, we're specializing to the case where there's no acceleration in the x direction. X usually means horizontal. And in the y direction, I have an acceleration equal to negative g, where g is equal to 9.8 meters per second squared, more or less. And if I plot x position and y position in a two-dimensional plane, it generally comes out to be a parabola. Okay. If you have had physics before, say a high school physics class, this might be a good time to go back and look at that section of the chapter. Okay. So we've got basically the physics that we need for the next question, which is the following. Say that you've been given the task to design a computer game, okay, where you're this little creature in red over here, and you've got some kind of ball lightning ray gun that you use to shoot some other kind of monsters. Maybe this kind of monster here. Okay. And we'll say that the dynamics proceeds according to basic projectile motion laws, like what we had in the previous slides. Okay. So that means that whatever velocity that you shoot the ball lightning with, you have to adjust the angle so that you hit the monster. Okay. So if the person playing the game sets the initial velocity to one thing, what is the angle that they have to use to hit the monster? Okay, let's say that we know the X position of the monster and the Y position of the monster. Okay, so maybe you have a scenario like this. Here's the protagonist of your game. And if you shot a ball lightning ray, it would follow a path like this, like okay. It starts at a particular angle and with a particular initial velocity. Okay. And as you vary the angle, you get closer and closer to hitting this little green thing here. Okay, so the computer program has to translate the angle that the player adjusts on their joystick into a trajectory like this and tell you whether the ball lightning actually hits the monster or not. Okay. So that's your goal. So first thing to do, of course, is to draw pictures. Remember, I emphasized you need to start by drawing pictures. I would go ahead and put some labels for the angle and for the initial velocity like this. And whenever you've got something where you draw pictures, you usually want to draw things like axes. That means you need to choose an origin. So let's make the point x equal to 0 and y equal to 0 to be the point right here where the ball comes out of the gun. Okay. So that should get you started. Okay, so what you need to do is take as input an x and y position for the monster relative to this gun. Okay. And then figure out what combinations of initial velocity and angle correspond to a hit, a successful shot at the monster. Okay, so we'll start by assuming that the initial velocity is some fixed number. Okay, say that it's hard-coded into the game. Then ask what is the angle necessary to hit the target. Okay, so this is your first challenge, the first thing for you to do on your own. Okay, maybe we can build up from there. But the first thing to do is see if you can follow the steps that I encouraged you to follow last Thursday. Okay, identify physical principles. Okay, we sort of already did most of that. And the relevant equations we also did. But it would be good if you guys make your own set of diagrams. Okay, and figure out how to do commenting and so on. So what I have in mind here is go back to my slides. If you've got copies of my slides, which you should be able to get on the website, go back to everything that I said here. Okay. Maybe watch my videos again and remind yourself what I said. I said draw diagrams and write pseudocodes. And I gave an example of the kind of diagrams that I have in mind. Here was one where I sort of alluded to projectile motion already. So you might want to draw something like this, but try to flesh it out more, fill in more of the details, and make it more specific to this particular computer game project. Okay, draw something like that. Remember that you need to make a bunch of comments. Okay. Now to fill in and do this calculation, you've got a little bit of a math problem that you need to start out with. We identified some of the basic principles, but you need to figure out how to further formulate the problem before you can fill in the code. So you're going to need to take a little bit of time to figure out how to translate in equation form. So just on a piece of paper, okay, let me in this so I can scroll. On a piece of paper, you're going to need to convert. You're going to say, well, what do I know? What do I don't know? Remember, that's one of the main steps. Figure out what you know and ask yourself how you can translate that in what you want to know. So you know the initial velocity, and you're assuming that the computer program gives you the X and Y coordinates of the monster. And you need to take that, which is what you know, and translate that into an angle. And then what would be great is if you could visualize the output by going even further and charting the trajectory of the projectile after it comes out of the gun. Okay. So see, as a first step, if you can translate the X and Y position of the monster and the initial velocity into an equation for the possible angles that you can get. That'll be step one. Okay. Then you want to fill in code, and I would like everybody to make sure that they fill it in with copious amounts of comments. If you'd like me to look at yours, I can look at it. And then to have a nice visualization of the output. So I know there are some example codes showing how to make plots and so on in Project Zero. So see if you can use those skills to show what the output looks like. And just to give you a sense of what to look for, this is a set of different combinations of velocities, initial velocities and angles that hit a particular point. So say that the monster is sitting right here at about 5 and 1.5 and whatever the points are in this computer program. And then I scan through a bunch of different initial velocities and figure out what angles are possible. And you see something like this. You see they all intersect the same point, but they all have very different shapes. Okay? Okay. And you can see what happens as I change the height of the monster, change the position of the monster in the horizontal direction, what the shape of those different trajectories looks like. And I can even plot how they even make an animation for how the ball lightning varies in its position depending on time. So if the ball lightning obeys ordinary projectile motion laws, this is kind of what it looks like. So some of the lightning gets to the monster first. That might be the trajectory you want to follow. If there's danger, the monster will run away. And some of them take longer. Okay. So what we're going to do now, hang on just 1 second. Okay. Okay, so what we're going to do now is we're going to separate into breakout rooms and encourage you guys to do some work together or on your own, do your own work and communicate with us with how it's going, ask us questions. So what we're going to do is we're going to have one breakout room dedicated to helping people who still need to sort of just get the basics, catch up with, say, software installation, or just, say, making a graph without necessarily diving into this project that I presented for you. Okay, so that will be breakout room number 1. Okay, so if you're still just struggling to set those things up, if you have questions, again, if you're wanting to ask some of these coding questions, maybe go to breakout room number 1. The rest of the breakout rooms will be dedicated to helping people get going on this project. Maybe take a little bit of time to do it on your own, and we'll have TAs and me going into these breakout rooms, providing some help. And don't forget that there's also the Slack channel that you can ask questions in. Okay, so with that, I think we'll switch to the breakout rooms, unless there are any urgent questions that I need to address right away.
Ted, given the structure that we have, do you think it makes sense to break out into many rooms, or perhaps we should just break out into one room and keep the stream live? Perhaps some of the people stay here and talk about this problem, and then have another session where people that are struggling to set up Python and everything else can join that session instead of having multiple breakout rooms?
Sure, that's a good idea.
Okay. I don't know if there's any questions that perhaps are relevant for everybody, except maybe one. We've been getting a lot of questions about whether we can provide a syllabus, or asking what is the assumptions that we're making here about the participants, if this is for beginners or what it might be worth, what this course is for. And perhaps just to remind people, I gave an introduction into the course last week, where I gave some lectures and explained that this is designed to be a course that is meant for beginners, people that do not have much background in programming. And so if you haven't seen that lecture, go back, and I will give you some context. I'll also explain that we were not going to be using a textbook, that we're going to be providing slides and all the material that we're going to be using in the class, we're going to make available for you. There's really no good textbook that teaches Python and all the physics tools that we're after. And so the goal is to give you tools that will get you to the point where you can do research and data analysis and so forth. There's nothing like that for beginners. I think the rest of the questions we can maybe address separately, individually, for people that are already in beginning session, that are still struggling with setting up their Python and very basic stuff, and then people that are ready to jump into this problem.
So let me just remind everybody that there are many places on the web with very clear, very basic introductory level tutorials and so on. I just provide one. Here's what it looks like. You can just go in and search for many of the questions that you would probably ask us. You might be able to figure out just by looking at this page. If you go to my slides and click a link there, you have stuff like this: control flow tools, if statement, for statement. Click on that and you can see a whole bunch of examples, right? Probably just by doing a search, you can find many of the answers to some basic questions.
There has been a question that a few people seem to have asked about the Python distribution you're using. You're able to change the parameters in real time right then and there. I think you changed height and initial angle or something like that. That's not available naturally in Spider. Could you, or some of the other distributions, can you comment on that?
So actually, this is not, this that I showed here, I did in Mathematica, just to show an example of what the result looks like. I can show you my Python code. We did some similar things in Python. Let me find them. It's probably best to build up to that. Okay. So here's what the output looks like in Python in Jupyter. And all I've done here is just make some graphs. And there are ways to make animations as well. And I'd have to look around for those animations. But I would suggest first just get some basic graphs like this. Then we can discuss how to make the interface more dynamic. Anything else for now?
Yeah, there was one quick question regarding clearing terminal. In order to clear the terminal, there's two ways to go about it. If you are in the like Python space that he's working with right there, as you see, you can type Control and L at the same time, and it just keeps you within the Python, the IPython range, and you can start over again with new definitions. However, if you're like running programs and stuff outside of a Python space, like in the original brand new terminal, just type the word clear and it clears everything.
Okay, so shall we break into a breakout room and then we'll keep this space open. We want to maybe give people a chance to sort of get started trying to work out these equations and so on. So I think what I'll do is I'll go to Slack and I'll watch for whatever might be coming in there.
Sounds good. How about Ted? How about I go to another to breakout room number 1, perhaps with Connor.
Okay.
Try to answer people's questions on installing Python, because I think some people are still struggling on the very basics. Does that seem reasonable?
Yeah, that sounds good.
Connor, are you on the call?
I'm going to stop sharing my screen here.
Sounds good. All right. I'm going to go to, so if you want to learn how to use just if you have questions about installing Python, about getting to use it, about defining functions, any of these things, just go to go to channel number 1, and I'll see you there. Okay. And maybe if Connor is not on the line, somebody else, Alex or Greg, one of you maybe wants to join, or maybe Fatma. I think Fatma's on the call, right? So maybe Fatma can join. Okay. I'll see you guys later.
We've been getting some requests to pop the kinematic equations up there for reference.
Oh, okay. What would be a good way to do this? I can just, let's do this. Maybe this is what you want. Okay, I'm going to step out for 1 second. I'll be right back.
I just want to quickly remind everyone that if you're still having difficulty setting up Python or installing Anaconda in any way, shape, or form, that's going to be addressed in breakout room number 1.
For those of you with us, feel free to ask questions on the live question forum, the live question feed, or the Slack platform, whichever is easiest for you guys. So just a question from Ahana from Virginia Beach. What would be a good starting program? So if you've done on that work, go ahead and you select either Jupyter or Spider. Jupyter would be best because it seems to be what most people are familiar with. I personally use Spider. It's basically a matter of taste at the end of the day.
We just noticed that you're asking whether we can start work on the project in this chat or in one of the breakout rooms. The only breakout room that's currently active is for setting up Python, so you can work on the project here, and feel free to ask questions about the project in the chat here, and we'll be able to respond to them here.
So I think maybe it would be a good idea for me to just print this page so everybody can just have it at hand. Is there a way to put that on like the website or something so that we can use my desktop for other things?
Assuming everyone has Slack, I'm pretty sure we could put a screenshot of this in the Slack chat.
Okay.
I'll work on that.
We could also upload it to the Dropbox.
Yeah,
maybe
that's true.
with the other slides as well, because quite a few people were asking for that.
Okay. Go ahead and do that.
All right, so I noticed two questions coming in regarding the math for finding theta, and asking whether we are establishing an initial velocity or if it's a constant. Part of this project is to determine the initial velocity required to hit the monster. And as for, is there a formula for theta? It's currently the task to find the formula for theta that you will draft up.
Right. So to start out with, hang on 1 second. To start out with, assume that V0 is dialed in, so you know what V0 is, the initial velocity. Okay. And then you have to figure out what angle you have. So you could, the other way, you could say that the angle is fixed and then figure out what velocity, if there is one, what initial velocity, if there is one, actually hits the target. Okay. So as you see from the pictures that I showed before, there are many combinations of angle and velocity that will hit the target. Okay. But as I write in this slide, let me show it again. Second. So you see in this slide, I say, start assuming that V0 is fixed. So that's given to you. And then you need to figure out what the angle is. So you need to figure out an equation for the angle in terms of V0 and the X and Y positions of the monster. Okay. And it might take a little bit of exercise in your trigonometry to get that equation. That's kind of part of the project. Okay. Okay, so let me deal with this, printing this set of slides.
Let's see. So, Buza from Kosovo asks, what are all the libraries that we need for this problem? It'd be helpful to use NumPy and Matplotlib, but also if you could import math, that will help you in defining one of the trigonometric functions as well. But I think NumPy should do everything for you as well.
Right. So I'll just copy and paste what I included. Close it. So I'm putting here in Slack what I included. Okay, so I've put in Slack those two slides. If there's an easy way to put those on, let's see, I can put them in, try to put them in Dropbox if I remember. Dropbox folder, I have like 7 windows open by this point.
So there's a M. Soto Rivera from Puerto Rico. He asked, is there a way to make Anaconda launch faster? Unfortunately, there isn't. It's painfully slow to open up my computer as well, and I've got a new computer, so kind of just have to sit and suffer through that. And I did get another question from Jesus Ricardo Rodriguez Valerio from Mexico. He says, hello, good afternoon, thank you for your dedication. I did not get why and how to use the library NumPy. So if you have access to the Slack, you can see exactly how to import libraries, set them under a different name to make them easier to use. But the syntax is simply just the word import and then the library of choice. So import NumPy or import Matplotlib.
And to follow up on what Alex just said, why we're using NumPy is because it's a library that contains many of the functions that you see, such as like square roots, that'll be seen in the final equation for theta.
So I just put those kinematics slides in Dropbox under the Project 1 folder. If everybody could look and make sure that they can see them. Good. Here's the name. And I also sent them on Slack.
So a question from Ricardo Yara from Mexico. Do we know the position of the monster alien, and is it fixed or it can be moved? So the idea is that yes, you do know the X and Y positions of the monster you're aiming at, as well as your X and Y positions, which you can choose to be a little more flexible there.
So following along what people are saying in Slack, okay, there's several things in Slack. So yes, what you need to do is figure out the angle of the gun, and it should be in terms of the initial speed, the initial magnitude of the velocity, and the initial or the position in the X and the Y direction of the monster. Okay, and I give some hints here. You will need to use a bit of geometry, okay, or a bit of trigonometry. You'll end up with an inverse trigonometric function, and you'll have to use the quadratic formula. Okay, so that means that you'll have generally two solutions that you have. For each v0, there will be two solutions. There's a question, how do you factor in time? Well, actually, what I'm going to tell you is that you first want to eliminate time, because what I'm asking about is just the path of the trajectory. I'm not really saying, I'm not asking questions about when the lightning ball is at a particular place. I'm just saying, does it actually pass through a certain place? So I would suggest that you figure out a way to eliminate time from these equations. So first, resolve everything into components, okay? Since I want you to specify an angle, you need to convert components into expressions with magnitudes and angles, okay? And then eliminate time from these equations. And if you go through those steps, hopefully you'll start to get an idea what you need to do.
So to clear us a couple things up that we're seeing on the live feed for questions, you are not writing a program that solves for theta. You are solving for theta by hand and producing the plot for the trajectory. Additionally, Ximena from Mexico asked whether it'd be better to use Python 3.7 or 2.7. In order to follow along with what we're doing within this course, you're going to need Python 3.7. However, if you have more questions regarding installation and that type of thing, I encourage you to head over to breakout room 1, where they'll be handling that side of things.
To answer Akhilesh Mugund from, by the looks of it, Pennsylvania, he asks, is it possible to put up the problem statement up again or in Dropbox? It should be available in Dropbox under, hold on a second, under the project number 1 folder.
Okay, so I've just put all of the slides for today in Dropbox under project 1. So if anybody has any trouble seeing them there, could you please let me know? Okay, looks like things are going well in the Slack discussion. If there's any trouble following along what's happening, please let me know or let somebody know.
So the files should be working. I have access to them at least, so that means everyone else does. So, German Roberto Chaidez Valdez from Mexico asks, "Hi there, what's the difference between an error bar function for plotting and a normal plot?" The error bar allows for some additional information to be put onto the plot, such as the error of the data values you've gotten. If you don't include those data values, that is, if you leave that empty, they actually function in the exact same way. So there isn't a difference, but do look online for the syntax of how to use the two, because the error bar function does expect y error and x error value inputs. So Deha Alexander from Chesapeake, Virginia asks, so how do you get started on the project? I am confused. Just to recap where we're at, if you go to the Dropbox and look at the project number 1 folder, you'll find slides including the kinematic equations that we're using. We want to use those kinematic equations to solve for theta without any time dependence in the solution. That's the first step of what we're doing.
So from the discussion on Slack, it's evident that people are hard at work on this bit of algebra, which is good. Don't forget to make a nice flow chart, a nice diagram of how you want the program to go. So how about we have a competition, everybody draw their own diagram like what I drew in my slides, right? One that looks like it's been drawn by hand. See if you can do a more detailed version of that tailored to this project. And if you like, go ahead and send it to me, and we can see how that's going for you guys, because that's a very important step. Okay, I'll return in just one.
I'd like to address a few questions that are on the live feed for questions within this program. First off, we are going to help you through this project later. So if you're really stuck and you're more focused on the coding aspect over the physics aspect, we will be addressing that going forward. And second off, there's another person who asked if they could post unrelated code in the Slack chat, or I believe you also mentioned the Dropbox. If you, I believe it's all right if you were to put something on the Slack, and we might be able to tell you what direction you're working along with. If you are writing, I think you said you had simple projects on the subject, and I think we'd be able to take a look at them if you put them on Slack.
Okay, so I'm going to pick up here again. Let me get some slides to show you guys. So you have all been struggling, which is good, struggling with trying to organize these equations in a way that allows you to write a program. Don't worry if you couldn't get the answer, or if you couldn't even get started, since we have a limited amount of time. That's to be expected to some degree. But I did want to give you a chance to struggle, just to develop a sense of how this works, this whole process of developing a project. Okay. But in the interest of time and in the interest of minimizing frustration, let's go through this together. Okay, so you have the set of equations. They're available on the slide, so I hope everybody can see the equations for themselves on the slides now. Okay, and refer back to them so I don't have to show them at the same time as I'm showing these new slides. I'm about to show you some new slides. So maybe keep those open on your screen at the side of the page. And let me share with you something else here. Let me just organize my desktop here a second. Okay. Okay, everybody see these slides now? Okay, now these are things that I drew by hand, and I'm purposely showing you hand-drawn stuff to encourage everybody to take an informal view of this. Okay, you should be doing this yourself. Take out a piece of paper and write down equations yourself. So I start by drawing some pictures. You see here. Let me get my pen here a second. You see my picture here. I drew a ball lightning gun here, and I make it look all cool because that's important. Okay, because otherwise it's not as fun. And then I draw some axes here, an x-axis and a y-axis, to say where I take time equal to 0 and position equal to 0 to be. So the ball lightning starts here at time equal to 0, starts right here, at position x equal to 0 and y equal to 0, and it comes flying out. There's this red ball here is the ball lightning with motion lines that I've drawn. It comes flying out with some initial speed, v0. V0 is the magnitude of this two-dimensional velocity vector, and it's going to arch over and follow some parabolic path like this. Okay, and this makes a pictorial representation of what I just said before, the list of things that I know. I know that there's going to be a monster over here. So let me draw a picture of a monster. Monster has a frowny face, so I draw a frowny face as well as I can using my my laptop. And there's some time t where this path intersects with the monster. Okay, I don't know what that time is. That's one of the things that might be a point of confusion when you first start writing down these equations. You have these equations with a t in it. You say, what do I do with that time? Well, we want to get rid of that time because we don't know what it is. But we do know that it intersects over here at some delta x. Okay, and some delta y. Like this. Oops. Let me undo that. So here's the monster. And that's right about here. That's delta y. And this is delta x. Sorry about my poor drawing here. This is the first time I sketched directly on a PowerPoint slide. Okay. So we know what that delta x is and the delta y. We know what those are because that's what's recorded in the computer game. And you need to get rid of that t. Okay, so you should draw a picture like this whenever you're doing this. Sillier the picture, the better, really. And we know what this initial speed is. Okay, and given that picture, let me just redraw the picture up here in the corner to keep it visually on hand. Okay, look at my list of equations. I know that delta x, that's going to be basically this, whatever the final x is where the path intersects with the monster, minus the initial x, which in this case is 0. I can call that delta x. That's equal to the initial speed in the x direction, the initial x component of velocity, times the time that it takes to get there. And by just a bit of trigonometry, I know that that's equal to v0 cosine theta. Okay. Now I could get rid of the time if I had two equations where I know everything except for the time. Then I could eliminate time between those two equations. I do have that because I also have a similar equation for the displacement in the y direction. It's like this. And if you, again, look at the slides that I posted and sent to you, okay, I have the exactly analogous equation. The acceleration in the y direction is minus g, so I have a minus g over 2 in front of that t squared. And then the v0y, that's the initial y component of velocity, just using basic trig, that's v0 sine theta. Okay, now let me just slide all of that up at the top of the screen so I still have it at hand. I note that I can solve this equation for time in terms of things that I know, namely delta x and v0. Okay, I don't know theta, but I want to get theta. I want to find an equation that is an expression for theta. So I'll keep that in the equation. And I can put that time, I can put that time back up here, here, and here. Okay, and get an equation that involves delta y, delta x, v0, and theta. Okay, so everything in this equation I know except for theta. So now I, in principle, should be able to get an equation for theta in terms of delta x, delta y, and v0 if I just rearrange this equation. Okay. I'm trying to go through this slowly enough that you can at least reproduce this later and when you watch this again. Okay. Maybe a few more trig steps that you need to do. Okay, so I'm again going to slide this equation up at the top so that we have a record of what we've already done. Okay. Sine theta over cosine theta, that's tangent of theta. And I've got a 1 over cosine squared theta here. So this is a point where some people start to get confused. I have a nice equation, just repeating what I just said. I have a nice equation that involves theta here and here, okay, and delta y and delta x, okay, and I want to solve for theta, or at least solve for, say, a trigonometric function of theta, okay, but I've got a tangent theta here and a cosine theta squared here, so maybe that's a little bit confusing until you note that tangent squared of theta, well, that's just sine squared theta over cosine squared of theta. Again, I'm taking my last result and just sliding it up the top of the page to keep it on hand. And sine squared theta, we know that that's equal to 1 minus cosine squared theta. It's a standard trigonometric identity. Or being very pedantic, that's 1 over cosine squared theta minus 1. But look, here's where I have a 1 over cosine squared theta. And so if I'd like to have this equation just involving one trigonometric function, I can replace this 1 over cosine squared theta with 1 plus tangent squared theta. Okay, let me go ahead and do that. I'm going to do this substitution, 1 over cosine squared theta into that equation. Okay, so again, I'm sliding everything that I already figured out up to the top of the page so I can keep working on it. And then I've got an equation that involves delta x and delta y here, here. And the unknown thing is tangent theta. So it's basically a quadratic equation in tangent of theta. Okay, and you know how to solve quadratic equations. Use the quadratic formula. Maybe rearrange the equation a little bit to make that easier. Okay, just plug that into the quadratic formula to solve for tangent of theta. And you should get something like this. And then you always put a nice smiley face when you get what you want to make yourself feel better for getting the right answer. So I think somebody got basically this result for their answer. Remember, the quadratic formula always has, or usually generally has, two solutions. We maybe want to think about what that means. That means that if you fire the projectile out of the lightning ray with a certain initial speed, there are actually two angles that you can use to hit the monster. And it's a good idea at this point maybe to step back and think if that makes intuitive sense. Imagine you're doing it yourself. You've got like a baseball or something, and there's like a can sitting somewhere on a target, and you want to throw the baseball and hit it. You could either try to throw the baseball in a kind of line drive directly at the can, or you could try to pop it straight up and have it go up and then come back down. Okay. So those are the two kind of solutions that you have. So that's the end of these slides, and we'll put these slides in Dropbox so that you can have them available. Do I want to keep, excuse me, my ink notations? No, I don't. Okay. So now that you have the equations, you just need to figure out how to integrate them into the computer program and to do the visualization. So we've gotten through the basic steps now. Okay, look at the steps that I outlined here.
So the question is, how do you guys share your code with us? How do you share your results?
Okay, identify physical principles. We basically started with the physical principles. Normally, you might have to do that yourself. You figured out the relevant equations. Now we organized those equations into something that we can use to make a program. So how do I integrate those equations into my flowchart diagram? That's the next step. Figure out exactly what you have to do in the program before you start typing out the computer code. Okay. So that'll be your next step. You now have the equations. Maybe make sure that you understand them. Go through and do that. Repeat what I've just done. Okay. And see if you can get started just solving the equations. But really make sure that you make a nice diagram. I'd be happy to see diagrams that people make. And say, what do I do? I start with some delta x, delta y, z0. Those go into the equation and then produce some output. Okay. See if you can organize it yourself, and we can all discuss it together. So again, maybe I'll just flash my code and stop sharing the.
Sorry to interrupt. We are getting an audio.
We're going to start sharing the PowerPoint slides. And I'm going to share my screen.
We're getting audio cut in on top of you. It sounds like Raul's feed. We're not sure where that's coming from, however.
So again, here's what my code looks like. Some important elements missing in this code.
I really think that's it.
I'll give you a second to see if you can see what's missing.
It's somebody else asking about
Something really important that I made a big deal about in my PowerPoint slides. What am I missing? I'm missing comments. In fact, I should have a gigantic comment section here at the top of this notebook with a detailed explanation of what this program is and what it's all about. Nice thing about Jupyter is it has its own sort of markdown language. Okay, so for example, I can make a cell like this and say something like ball lightning, okay, and give a description of what it is. I'd like everybody else to try to do that before I do it. Okay. Note that I've got these libraries that I've imported, so I might even say that. Importing libraries. Note that one way to indicate comments is to put this kind of hash pound sign in front of some text, and that identifies it as a comment. Or if I go into a cell, I can do cell and then change cell type to from code to markdown to make that yeah, I did just type text. Okay. And you might see some things here that look familiar given the little bit of algebra that we just went through. A del x plus and a del x minus. Just del x is my way of writing delta x. It's maybe not the best.
Ted?
Maybe not the best identifier in the world, but basically corresponds to delta x. And ultimately, I've got two solutions for a given initial velocity. Then I've got several initial velocities with a particular solution. You can see them all going to the same point where the Martin scale is. And maybe once you get used to just making these graphs, you can make them a bit more elaborate, having some dynamical interaction that allows you to change v0 in real time. Okay, but see if you can get something like this before next time, or maybe next time we'll work on getting something like that. For now, I think I'll just pause. We have just about 6 minutes left, so let me pause and let the remaining questions come in. And also, anytime before next time, if you want to send your diagrams to have us look at them, or maybe snippets of code even, feel free to do so. Is everybody hearing me now?
Yes, clear now. Can you hear us?
Feel free to do so, and we might not answer right away, but at least next time we'll have a list of things we can discuss. Is my little bit of algebra there crystal clear? Are there any steps that I need to go over again? Okay, so I think I'll just wait out here the rest of the time for any questions to come in.
Can you hear me, Professor Rogers? Not yet.
I could hear you, Alex.
Okay, I got a question about whether the code that I just showed would ever be posted. Yeah, I think I'll post it eventually, but I think it'd be a good idea for you guys to wrestle with creating your own version for a little bit before we do that without that there. But of course, eventually I'll show you exactly what I've done at least. Maybe some of the TAs also have some good suggestions. I got one question that we notes that we use some trigonometry here, some significant trigonometry, and the question is whether you will need to know trigonometry or other high-level math for the other projects. So I think none of the other projects that we have in mind will involve the level of trigonometry that we just did here. And any math that goes beyond algebra will go through the details ourselves at some point. So for something like this, for example, I wanted anybody who had trigonometry to have a chance to wrestle with setting up these equations on their own before I gave the answers. But if you don't know trigonometry, it's totally fine. Just feel free to just take my answer and assume that when you get to studying trig, you'll learn how to do that. The idea was that anybody could at least follow what we're doing here. At least in the sense of in setting up the Python code and so on. So my idea was really to have something that people could get a little bit of a challenge out of if they'd had trigonometry, but it would not be a complete roadblock to those of you who haven't. And any other kind of math that we use that goes beyond, basic algebra will be presented in the same spirit. Okay. Okay, so it is now 3 o'clock, which is the end of the time period that we've got set aside. So unless there are any really pressing things, we'll pick up next time. We'll continue to work on this project for a while. You've got the equations now. I would urge everybody to try in the meantime to do this themselves if you can, if you've got time. You've got the equations now, you've got the basic tools, I think, to start putting together Python code. So go ahead and get started if you can, and we'll discuss next time. Should probably stop.